is the orderly state for the data buffering, which is actually the topic I'm going to focus here. Within the next 20-ish minutes, I'm planning to recap some basic concept of the state and how Beam handle that. And I also will talk about the orderly state and why we need them. And after that, I will briefly introduce the APIs and also have a walkthrough on an example and present you the pseudocode. At last, if time permits, I will try to do a short demo and show how it works. And so this talk is mainly focusing on the orderly implementation in Python, so which I think is just the person who asked like in the last session. So let's start. I may use some terms interchangeably, like data points, events, elements, so they all mean the same thing. And transforms or data operations, they all also mean the same thing. So sometimes these terms just slip out of my mouth. Okay, when we process data, so we can categorize the data operations or the transform in Beam's terms into two basic categories: the stateless and stateful. Stateless operations solely depends on the current event itself, and maybe some global ground truth. The examples are like splitting the input strength by white space, for example, or converting an IP address to its geolocation. On the other hand, stateful operations depends on the current event as well as the information from the other past event. For instance, you want to compute the moving average of a matrix in the last in the recent like 10 minutes window, or some advanced online learning algorithms that we want to train on the streaming data. To put things a little bit in a mathematical form, stateless operation like f on the left can map an input of x to the output of y independently, while a stateful operation like g on the right takes the input x of the current time and another internal variables of s from time t-1 and produce the output y and another version of the internal variable st. The internal variable here is the state we call for the stateful operation G. And in short, states are the information derived from the past event, and the operator, the operation executor has to remember to process the current event. So in Apache Beam, we provide different state classes for users to store different type of states. To make things clear, so when I say state in Beam, I really mean these state classes or the data structures. So there are a few properties for this state. The users must provide a unique ID and a coder. The unique ID apparently are used to tell Beam which state we are working on, while the coder is needed for serialization and deserialization of the state values. States are per key per window. Again, states are per key and per window. So for a given window, by default, we are using like the global window. The events with the same key will share the same state. And states are also local. It will be accessed in a single thread. There won't be any states sharing between different threads or between different workers. So this is kind of like a simplified models we have, or the simplified programming patterns we have in Beam. While the APIs of the states are pretty much standardized, the implementations is runner dependent. Here is a Python example for a stateful do-fun. It used the read, modify, write state, which is also known as the value state in the other Beam SDKs. So this state is used to hold one single object in the cell. So you can see the ID here and also the coder defined here in the definition. For value state, the supported operations are simple but essential, like read for reading the state value and write for overwriting it with the new value. And so here comes a question. So given that the value state is so powerful, so it's true or false when I say we can use a value state to represent like anything we want to store as a state? What do you guys think? So just like the ancient people said, give me a lever long enough and a standpoint, I can move the Earth. Is the value state the only one state that we need after all? It is true, technically, as long as we have a coder. As I said, we need the ID and coder to define the state. So as long as we have a coder for this object, we can store it in the value state. And it provides read and write, and that's the enough APIs we have, right? However, there are other aspects that we need to consider, such as efficiency, which is extremely important in the data processing, especially in stream data processing. To answer why we need other states, so we need to know how states are handled in Beam. So here on the left, we can see there are the three major components in the Beam data processing pipeline. So we have SDK client, the runner, and SDK worker. And let's assume that we define a pipeline in which there is a stateful do fun. And notice here, the default value of the state variable defined here is actually placeholder. The state POM only includes information of a state spec. The state ID coder is actually those basic information, metadata. So first, the user pipeline is converted to the proto via runner APIs, and then the stateful do fun is part of the proto. The proto is then sent to the runner via job APIs, and the runner sends the work to the workers and communicate with them via fun API. Let's zoom in this part, like the operation between the runner and the SDK worker to take a look at it, take a closer look at it. So the runner, the SDK worker, to process a bundle through instruction request, which contains something called the process bundle descriptor ID. So this process bundle descriptor is for telling the worker what and how to work. If this descriptor is not in the worker cache, so the worker will request it from the runner. The stateful do fun is part of this the payload there, and it gets passed from the runner to the SDK worker. Now the SDK worker unwrap the stateful do fun. Before it executes the do fun, it will first check the arguments. And if it sees there's a state placeholder, and it will replace it with the actual state object. So in general, we will have to serialize and deserialize the state for each bundle. For value state, let's go back to the previous example, like we use word value state. This means that we need to serialize and deserialize the entire object. Of course, we can do some smart caching on the reading part, but the writing part is inevitable. In case of like worker crashing, we have to write the state back to the runner. So we also noticed that for different state type, we can actually provide, Beam can actually provide a richer set of interface, more than read or write. So in this case, users do not need to reinvent the wheel and implement those functionality on their own. Furthermore, Beam can do some optimization on the operations based on the property of the data structure. So in short, for better efficiency and ease of use, Beam provides not only the value state, but also a handful of other states for users to use. With the multiple states available, users need to choose the right state type. Currently, Beam supports 7 different types of state classes. I like to visualize them in the map, in the tree diagram as shown here. From top to bottom, the state go from generic to specific. From root, we have like the most generic state, as I said, the value state. It can literally represent everything. If we have associative and commutative combined functions, we could probably try the combining state. Back state is the best fit for a list of elements, while the set state and map states are good for unique keys and key value pairs. Multi-map state is a more specific map state that supports multiple values on the same key. And the orderly state is, that's this topic here, is specifically designed for storing key and value pairs whose keys are timestamped in order. For example, if a user wants to store a list of elements, they can put in the entire list as the value state and use a list coder, right? And the implication, as we mentioned here, is we have to serialize and deserialize the whole list of elements for each of the bundle. But if we use backstate instead, Beam optimizes the write back part in an incremental update fashion. So that means that only the newly appended elements are sent to the runner instead of the whole thing. This reduced some of the cost we might have had if we had used the value state to store the list of elements. Likewise, if users want to store a list of elements ordered by their timestamp key, order list state will be the choice. So order list state have three APIs that are the same as the back state. They are add, read, and clear. The add API insert elements to the state. The elements in the order list state are key value pairs where keys can be timestamp or int64. So internally, keys are stored as int64 anyway. We follow the multi-map semantic where a key can associate with multiple values. That means that you can have a timestamp that have you have multiple entries with the same timestamp. The read API reads the current state. It may or may not retrieve the items from the runner based on whether the value is already cached. The clear APIs remove everything from the state, making it empty. Besides these three APIs, order list state also has its own API, the read range and clear range. So these two APIs support read and remove operations on keys within a half open range from here, for example, low to high, where low is included and high is excluded. So these operations are optimized for order list state. Notice that this operation can also be achieved with backstate or map. However, it will require user to implement their logics on their own, and most of the time there will be sorting, unnecessary serialization and deserialization process, making it less efficient. When we call read range, so this is also something interesting. So when we call read and read range, an iterator will be returned. One of the features in the order list state implementation here is that we design the operation of add, clear, and clear range so that it will not be invalidating by these operations. So I will show an example in my demo at the end. So in other words, so if you have an iterator and you haven't finished the iterations, but you have add or remove or those are modification operations in the middle, it will not change the behavior of the existing iterator. So we have seen these diagrams on the previous slide when we talk about how states are handled in Beam. This also gives us some idea of where the code we need to change in order to implement order list state. Again, we have three components: SDK client, runner, and SDK worker. To implement the state, we first need to ensure that in the number one point here, we need to define the APIs of the state. And then we also need to make sure that we define the proto to use to communicate between client to runner and runner to the SDK worker. And third, we also need to implement the actual SDK. And last but not least, if the state is not supported by the runner itself, we definitely need to touch the runner part to let the runner to store the state and also respond to the state request. Additionally, if it is a brand new state, we may also need to add a new URN for the state and change the compatibility check so that the URN is allowed during the pipeline validation. So here is the walkthrough example. So the left column here is persistent state in the runner, and the middle column here is the internal structure we use to implement the order list state. So if we have a read request here, so see we can read the empty order list. Now we try to add a few elements in there. So 2, 5, key with 2, 5, and 9, and we put them into the pending buffer internally. And if at this time we have a read request, so we will read the pending read. Now we have a clear range request to remove the keys from 1 to 7. And then we do the remove directly on the pending add. So in this case, so if there is no persistent values, you can see the return values is always the same as like the pending add. If there's something in the runner, I mean that is the persistent order list in the runner, what we want to do is, so there is a read request here, and we will go through the runner and get the persistent value. And if we add something to the list, we will add these new items to the pending ads collection. And when we try to construct the things that we want to return from the read, we will merge the pending ads with the things we have in the persistent storage. Now, if we want to remove it, we will remove the things that in the pending ads. And when we construct, and we are not going to remove the things from the persistent storage because it's persistent and we haven't synced the states yet. But we will do a filter on the persistent order list by removing the range that we said is pending removed and merge that persistent order list without these pending remove keys with the pending ads. Okay, so the pseudocode. For add, it's simple. So we pretty much just add into pending add. And for clear range, we operate it directly on the pending add, remove the things that we are about to edit. And we also put that into the pending remove, and just like it's a bookmarking. When we need to read the range, so there are two scenarios. When there is no persistent items, so we return the pending ads directly. But if there are persistent items, then we need to filter the persistent items and then merge that with the pending ads in range. So I don't have time to do a demo. But remember that I mentioned we support the feature of like not invalidating iterators on add or clear. So I don't have time to cover that today too. So if you are interested in that, so that will be like a homework for you guys to figure it out. So the rest of the slides are about the references, and thank you.